We're actually in a pretty good place now with symmetric matrices. We have originally shown that linear transformations that essentially scale the space along some orthogonal directions are always represented by symmetric matrices with a standard Cartesian caveat. We have also almost shown the converse, that symmetric matrices always correspond to linear transformations that essentially scale the space along some orthogonal directions. Now, how did we do that? Well, first, we stated without proving it, we'll prove it later, that symmetric matrices always have a full set of real eigenvalues and corresponding eigenvectors. But we actually proved that eigenvectors corresponding to distinct eigenvalues are orthogonal. Now we'll discuss the case of eigenvalues that are the same. In other words, eigenvalues whose multiplicity is greater than 1, as is the case in this symmetric matrix. Now we know from our easy giveaways for eigenvalues that 9 is a double eigenvalue in this matrix. Because first of all, 9 is alone in its column and it's on the diagonal. So it corresponds to the eigenvector 0, 0, 1, which I have as the second eigenvector here. Also, can you see the second giveaway? Well, it's the fact that every row adds up to 9. So all rows add up to the same number. That number, which once again is 9, is the eigenvalue, and 1, 1, 1 is the corresponding eigenvector. But of course, these two vectors are not orthogonal. What's their dot product? Their dot product is 1, not 0, therefore not orthogonal. Does this contradict any of the statements we made before? Of course, it doesn't contradict that, because our earlier statement applied to eigenvectors corresponding to distinct eigenvalues, not to the same eigenvalue. But these eigenvectors, we have some choice in choosing them, and we can choose them to be orthogonal. Why? Well, because these two eigenvectors belong to the eigenspace associated with this eigenvalue, and it's a two-dimensional eigenspace. Any linear combination of these two vectors is once again an eigenvector corresponding to the eigenvalue 9. So we can take any linear combination and we'll have another eigenvector corresponding to the same eigenvalue. So now we're going to appeal to our geometric perspective. Even though we're having an algebraic discussion and we're talking about R3, which are sets of numbers, and the algebraic dot product, which has maybe not much to do with the length of one vector times the length of the other times the cosine of the angle between them. Nevertheless, nothing can stop us from using our geometric intuition or geometric analogy. So we have a two-dimensional eigenspace. We can immediately think a plane. And we have a plane and we can choose any two vectors. Of course, we can also choose orthogonal vectors in that subspace. We can always just choose them arbitrarily or express them as linear combinations of two vectors that are given. But we're free to choose any two vectors in that plane, so we can always choose orthogonal vectors, actually in infinitely many different ways. And that's what we're going to do here. We're going to choose two vectors that are orthogonal from this eigenspace. So that vector could be chosen in a number of different ways, but we're going to replace this vector with the vector 1, 1, 0. 1, 1, 0. Okay, so now we have two vectors that are indeed orthogonal. Now their dot product is 0. So they're orthogonal to each other. And of course, by the earlier proof, earlier argument, each one of them, regardless of their relationship among them, is orthogonal to this vector, as you can check for yourself. So now we have a full set of orthogonal eigenvectors. So in summary, when we have a symmetric matrix, it always has a full set of real eigenvalues, and its eigenvectors are either orthogonal or can be chosen to be orthogonal. So symmetric matrices really are the best kinds of matrices when it comes to eigenvalues and eigenvectors.